Alright, now we're on to question number 4 in the 2019 B test. As always, feel free to pause the video and try to give this question a solve of your own before I go over the answer. Okay, so this question is actually deceptively easy. It's actually, I think, a lot harder than it seems. And the reason is because if we model, let's first model the case where one of the mass is held stationary and the other one is gravitating towards this mass, okay? In this case, obviously we have that the force is equal to ma, and the force acting on this one is just g, right? Gmm, because they're both of the same mass, divided by r squared is equal to ma. So then the acceleration of this guy towards this guy is going to be a is equal to gm over r squared. Okay, so if we're given the acceleration, then we can figure out the time it takes for it to actually cross, let's just call it delta x. Okay, so we might want to try to use 1/2 at squared. Delta x is equal to 1/2 at squared. However, a really big issue is because acceleration is not constant. As you can see, acceleration depends on the radius, and the radius is the initial radius subtracted by delta x. That's what the radius is, right? That's how far away it is from how far away these two masses are. So we actually can't use this equation, although it turns out even if you use this equation, you get the right answer. Instead, what we're going to have to do is we're going to have to model it like this. So the acceleration of the system is the second derivative of the change in the radius, right? As a function of time, and that's equal to g over r squared. So now we have this differential equation with these two as constants, g and m as constants, and then we have r as r squared here, but we also have d squared r over here. So what we're going to do, if we want to find r as a function of time, we're going to have to solve this differential equation. And again, the reason we're trying to find r as a function of time is so then we can just plug in r equals r going from big R to 0. That's going from this radius all the way to radius equals 0. So that's the time it takes for it to cross this distance. So I'll show you what I mean later. But how we solve this differential equation is we have to do it's kind of like a separable differential equation. If you don't have knowledge on differential equations, then I don't think it's too big concepts. But anyways, how you would do it is you would have to first set, so let's call v equal to, let's see, you would set v is equal to r prime, so actually I'll just write dr over dt. Okay, so that means that dv over dt is equal to d squared r over dt squared, right? Okay, so given these two, we can actually try to calculate exactly what is v. Okay, if we calculate what v is, then we could. This is just a simple first order differential equation. We'll just move dt on this side and then solve for r as a function of t. So how do we find what v is? So we know that dv over dt is equal to d squared r dt squared, which is actually equal to, if I'm just taking it from here, it's equal to g over r squared, right? Now, actually, there's something that we can do. If we just notice that dv over dt divided by let's see, dr over dt, which is just equal, like we can pretend that we're canceling out these two dt's. So dv over dr, that's actually equal to, sorry, this is actually equal to, so remember we set dv dt is equal to gm over r squared, so gm over r squared divided by dr over dt, which we set as v. Okay, so now we can actually separate this guy out, so then it will be dv, it's like I'm multiplying by v on both sides, so v dv is equal to g over r squared dr. So now if we just integrate both sides, this gives us v squared over 2. We don't have to worry about the constants yet because we can just consider all the constants in the end. V squared over 2 is equal to, so this will just be gm, so negative gm r to the negative 1, right? Alright, so now we actually have the equation for v, so let me just write this in terms of v. So this is equal to, v is equal to square root of negative 2 gm over r, right? Make sure I did that right. Yep. Okay, so now we have equation for v in terms of r, so we can solve for dr dt. So let's plug this back into here. So set square root negative 2 gm over r is equal to dr over dt. So again, we can separate this out, so then we get square root r dr is equal to, I'm just multiplying by square root r on this side, multiplying by dt on this side here, so square root negative 2 gm dt. So again, we integrate both sides, but this time I'll actually add some bounds based on the question itself. So what is r going from? R is actually going from the initial position, which is capital R, so whatever initial radius it's at, and then it's going all the way to the distance 0 because that's when the two blocks collide, okay? And at the same time, during that time, dt is going from 0 to whatever time it takes for it to collide. In this case, we're given that it happens in time t. Okay, so now solving this guy, we get square root negative 2 gm dt is equal to, and then this is so hold on, I'm not gonna write dt, what the heck, I'm gonna write just t, and this is equal to, so what is the integral of r to the power of 1/2? That's r to the power of 3 over 2 times 2/3, right? And this is from 0 to r, from r to 0. So if we plug it in, that actually is negative 2/3 times r to the 3 over 2. Okay, and this is equal to t square root negative 2 gm. Okay, so now if we just isolate r, actually, yeah, if we isolate r, we get negative 3 over 2 t, okay, times the square root of negative 2 gm. Okay, and this entire thing is raised to the power of 2/3. That's equal to r, right? So if we simplify this slightly, then we can get r is equal to, so actually I'll write this right here, whoops. I'll write this as to the power of 1/2. Okay, so this thing becomes to the power of 1/3, right? If we just multiply 2/3 times 1/2. But so then we get negative 3 over 2 t to the power of 2/3 times negative 2 gm to the power of 1/3, right? So then not out of space, but simplifying that, the final answer you get is r is equal to the cube root of 9 over 2 g t squared. So this actually is after we solve this initial differential equation we are given, which is this one right here. And this gives us, what does it give us? It gives us what the time it takes for in this case, just one gravitating block to cover the distance r, for it to collide, in other words. Okay, so actually let's isolate t in this instance. T is equal to the r cubed times 2/9 divided by g and then the square root, so to the power of 1/2. Okay, so this is actually an equation for t in terms of how far away it is. Now let's consider the case where the two blocks are both moving towards each other. In this case, the force on both of them is equal to ma, right? So we could write F equals ma for this one, and also F equals ma for this one. And then we get that the acceleration of this guy is equal to, so g, again, gm over r squared, and this one's also equal to gm over r squared, but in the opposite direction. But since they're coming together, we can actually, if we just set the reference frame to one of the blocks, say this one, that means that this one's just coming at 2 times this acceleration. So basically, if we set 2 times the acceleration that this one is moving at, right? So basically, we can also do the exact same differential equation right here, but instead of having gm as the acceleration, you will have 2gm, right? Because you have 2 times the acceleration here. And then if you go through the exact same process, it turns out that you're just only adding a constant to this equation. So you get t is equal to 2/9 r cubed over 2gm, right? And then this thing's to the power of 1/2. And everything is the same. So actually, I'll call this 1 and t2. Okay, so everything else is the same except for that there's this extra square root 2 here, right? So then we get that t2 is equal to t1 divided by the square root of 2. And that is this answer. T1 is capital T.